Okay, and a second example from this section, example 4.43.2, we'll take the contour to be C sub r, z equals r e to the I theta, theta ranging from 0 to pi. So this is the upper half. It's the upper half as shown in figure 47, upper half, upper semicircle of a circle of radius r. We'll let z to the 1/2 be the branch of the square root function. Z to the 1/2 is e to the 1/2 log z. They have to tell us something about argument here to explain which log they're using. And they're telling us they're taking theta values between negative pi halves and 3 pi halves. So this branch of the square root function is undefined for angles coterminal with negative pi halves. So the branch cut is from 0 along the negative imaginary axis. In polar coordinates, we can write this square root of r, e to the I theta over 2, expressing this branch of the logarithm in terms of natural logs and in terms of thetas. So that'll produce this with the constraint that theta is between negative pi halves and 3 pi halves, excluding the endpoints. Here's the picture. We're looking for upper bounds on integrals, no doubt. Got good news for you. This time the branch cut doesn't interfere with contour C sub r, so we don't have to worry about any of that piecewise stuff on this one. And the instructions are more explicit this time. Find a bound on the integral about C sub r of z to the 1/2 over z squared plus 1, taking the radius of the circle to be greater than or equal to 1, or greater than 1 strictly. Ooh, and show that the limit as r approaches infinity of that integral equals 0. Now, I can draw a little picture of that somewhat. So we're integrating over this circle. We're going to get a bound on the resulting integral, and then let r get large. When r gets large, we're taking integrals over larger radii semicircles. Must be, we'll use that bound to show as r approaches infinity, the bound must approach 0. And if the bound approaches 0, then the integral must approach 0. So first, we need a bound on the integral. Okay, let's see, z on the C sub r, it's a complex number of modulus r, then, and we're told r is greater than 1. So mod z to the 1/2, that would be, if we deal with this in terms of the polar coordinates, the modulus is capital R, so we'll get square root of capital R, e to the I theta over 2. That's similar to what we have up here, except now we know the modulus is represented by capital R. When we take a modulus, hey, the e to the I theta over 2 has modulus 1, so we lose that, and we're just left with square root of r, as you would expect when you take the modulus of a branch of the square root function. We get the square root of the modulus. Okay. Now about the denominator, z squared plus 1, similar to the previous example. We'll use corollary 1.4.1, which says z squared plus 1 in modulus is greater than or equal to the modulus of z squared minus 1 absolute value of. Modulus of z is r. Okay, so that'll give us r squared minus 1, knowing r is greater than 1. Tells you I can drop the absolute values because r squared minus 1 is then positive. That allows us to get a bound, capital M sub r this time, because we're letting the r vary, I guess. A bound on f of z, z to the 1/2 over z squared minus 1, and upper bound on the numerator was square root of r. A lower bound on the denominator was r squared minus 1. So your thing with reciprocals, that gives us a bound of square root of r divided by r squared minus 1. That's a bound on the modulus of f of z, so we'll denote that by m sub r. To use theorem 4.43.a, we need to know how long this contour is. So that's going to depend on r as well. So it's a semicircle of radius r. Circle of radius r has circumference 2 pi r. Cut that in half because it's a semicircle. We'll get pi capital R out. So the length is pi r of that contour C sub r. So we've got the length, we've got the bound, capital M. So by theorem 4.43a, the integral over C sub r is the integral over C sub r in modulus is bounded above by the M parameter, square root of r over r squared minus 1, times the length, times pi r. Simplifying a little bit, that gives us pi r to the 3/2 over r squared minus 1. Hey, all the r stuff is just real numbers. Don't freak out about branches of this of the 3/2 power function or something like that. We're in the real setting at this point, at least. Okay, so there's your bound that they wanted, first off. Now they want us to show the limit as r approaches infinity of that integral equals 0. Well, you know, the limit as r approaches infinity is less than or equal to the limit as r approaches infinity of the upper bound, limits preserving inequalities. Then we've got r to the 3/2 in the numerator, and r squared in the denominator, borrowing from your calculus 1 knowledge. Hey, the denominator is a higher degree than the numerator, so this is going to go to 0. If the limit of the modulus goes to 0, then the limit of the quantity itself must be 0. The only number of modulus 0 is 0 in the complex setting. So the limit of that integral must be 0 as well. And that takes care of that section and some of the examples. I'll see you in section 44.